Okay, I want to jump straight to 1.6 of functions because it's probably the most difficult part of the first chapter, and then I'll backtrack. But first, I would strongly recommend you get used to this tool, Desmos \calculator, and I would also suggest you get used to especially the two most common studied ones in the next 2 years of math. But also, you're going to have to get slightly used to this one, and this one. So I'll just turn them all off one by one. The line is the standard one that we're all used to and the easiest to understand. Parabola or quadratic function is the next one. The radical square root function, the absolute value function, and the reciprocal function. And you should know two things. You should know the domain and range of both these things, I guess 3 things, and 3 common points. For instance, the line you would go with -1, 1, -1, -1, 0, 0, 1, 1. Parabola I would go with maybe 5 points, the 0, 0, the 1, 1, -1, 1, and the -2, 4, and the 2, 4. The square root function, I would go with the 0, 0, the 1, 1, and the 4, 2. The absolute function is pretty straightforward. 0, 0, maybe 1, 1, 2, 2, -1, 2, and -2, 2. And by the way, if you ever forget these key points, you can just pull up a line. Let's say you forget the key points of a parabola, for instance, and you can just make your own T-cell table, put in a couple values for that parabola, and it will be marked. And then you can just have your own parent function key points. These are parent functions. In other words, all you need to know is to memorize the parent functions and then nothing else. So you just make your own T-cell, you put in some values of x, and then throw it into the formula to see the values of y. And then you have a graph of your own. You have your parent function key points. The other thing I would remember is the domain and range. So the domain of range of a line is XER and YER. Now there are some limitations. For instance, when you're using the line for the speed of a car, you would never have negative time. So x is always going to be bigger or equal to 0, and thus y is always going to be equal to 0. So it really depends what you're studying. However, the basic domain and range of a line is XER, YER. All parabolas have XER, but the range is dictated by the vertex, by the y value of the vertex, and whether it's facing up or down. So the range of any parabola is, in this case, is y is bigger or equal to 0. You include 0 because 0, 0 is a point on this graph. But if this parabola is facing down, suddenly the range, and by the way, a negative leading coefficient is what faces a parabola down, then suddenly the range is y is smaller or equal to 0. So keep that in mind. For a square root function, the range is limited by the domain because you can't have the square root of a negative number. You can have square root of 0, that's 0, which is why it starts at 0, 0, essentially the vertex. And you'll see 1, 1, because the square root of 1 is 1. And you'll see 4, 2, which square root of 4 is 2. What you won't see is any negative value of x because we can't take a value of negative values. Therefore, that's a limit on the domain. And as a result of having no negative x values, you'll never have any negative y values, which limits the range to this positive area. Therefore, the domain of this function is x is bigger or equal to 0, and the range is y is bigger or equal to 0. Absolute functions has a very, very similar domain range to a parabola. It's XER. And the range is y is bigger or equal to the y value of the vertex, and it too can face downwards with a negative leading coefficient. And you're going to discover they all behave similar ways, and that's what the point of transformation is. And this is the toughest one to remember. If we zoom out, and you would ignore the bottom, it would actually look like a flat line at y is equal to 0. It actually would look like that. However, it suddenly reaches this point and veers off course and goes crazy. And that's because you cannot possibly put a 0 at the bottom of a fraction. Your calculator will bring back invalid response, and it is one of the few impossibilities in math. which means as x gets closer and closer to 0, and any number at the bottom, here's another thing I want you to learn. When you have a fraction, 1 over 1, if I increase the top of this, the numerator, I can see the result gets bigger. If I increase the denominator, I can see the actual result gets smaller. So that's something I want you to keep in mind. As the denominator gets bigger and bigger, the overall answer gets smaller and smaller. As a numerator gets bigger and bigger, the overall answer gets bigger and bigger. And that's called indirect relationship and direct relationship. Indirect because as this goes up, this goes down. Direct because as this goes up, this goes up. And that's what a fraction does. I want you to keep that in mind. So it's clear that if I have 1 over x, if I bring my x closest to 0, I'm getting smaller and smaller, right? So if I take 0.001, my answer is plus 1,000. If I take negative 0.001, my answer is negative 1,000, which explains why as x gets closer and closer to 0 from the negative side, my y approaches infinity negative. And as x gets closer and closer to 0 on the positive side, my y approaches positive infinity. So you have this interesting relationship, x ER, y ER, but x cannot be 0 because we can't have that in a fraction. And as a result, you're never going to have a result here that equals 0. You'll get very, very close, but you'll never get to 0. And that's seen when you put a big number, a million in for x. The overall result is 0.000001. So we never quite get close to 0. And the other direction, as we get closer to 0, as we get negative x a million, we get very close to 0, but on the negative side. That's because, look, if I put 1 divided by a negative million, look at my answer, negative 0.001. So it's trying to get up to 0, but never gets there. You can also find these answers easily using Desmos, because if I put it in proper function notation, like this, and then want to find what f negative 1,000 is, or 10,000 is, it tells me right there. It's used to function notation. And all of these should be in function notation. I actually can't use e because it's a special number. If you want to do it properly. And that way down below, if I put like a of 4, I will get an answer for the function a up here instead of getting confused with the other function. And it tells me the result is 4. So get used to Desmos, get used to understanding the basic domain and range. Now, I'm just going to get rid of all of these and focus on the line. I want you to focus specifically, we're going to focus on what's called y transformations. In other words, it only affects the y values of this graph, and I'm just going to change it to f of x because we're going to use this a value. And when you're evaluating, if I'm looking for f of 3, what happens is it puts 3 in for x and solves it. So obviously f of 3 is going to be 3 in this case. I want you to notice what happens to this line. I'm going to do a table of values of the standard line here. And then I'm going to do another one down here. F of x is equal to x. Now I'm going to add a 3. I'm going to make a g of x so it doesn't confuse the two. X plus 3. And I want you to notice the same values that we took up above. I'm going to put x of minus 2, x of minus 1, 0, 1, 2. Find the results, and I'm going to do the same for this one. Now I want you to look at the red results. This is the parent function. I'm going to turn off the transformed function. And I want you to pay close attention. Let's just pay close attention to 0, 0. Now I'm going to click on the one that added 3. And I want you to look at what its middle point is. 0, 3. It looks like the y value, not the x value, went up by 3. This makes sense when we see what happens. No matter what we plug in for x, which is the same as what we plugged in up here, and we just add 3 to it, we're really adding 3 to the result, which is the y value. Let's look at some of the other spots on this graph. Let's look at this one. We have, I don't know why it's not staying lit. It should. But we have that minus 1. Now let's add 3 to the y value. It should be minus 1, 2. Sure enough, it is. Let's look at another one over here. Let's turn that one off. 1, comma 1, if I add 3 to the y values, it should become 1, comma 4. And it does. So we can see that when I'm adding something, especially far away from the x here, and you might say, what do you mean far away from the x? Or whether I put it with the x or outside the x, it doesn't matter. And you're right, for a line it doesn't matter, but we'll get into cases where it does later for different things. For a line, the line's so simple that you can't see the transformations, but I just want to focus on the x transfer or y transformations. And this is the easiest transformation to understand. I want you to notice something. I'm going to put plus a. Doesn't matter what a is. And I'm going to make a go from anywhere from minus 10 to 10 in steps of 1. And I'm going to hit play. Now watch what happens to my line. It goes all the way up to 10 and all the way down to negative 10 and back up. It's essentially adding. For instance, this is x plus 4. And we can see that the y value of its original starting point down here has gone up by 4. So no matter what I put it here, it's clear if I put a number that goes up, the line rises. And if I put a negative number, like negative 5, the line goes down. Negative 5, negative 6, negative 7, negative 8, negative 22, it doesn't matter. The line's going to go down and up. So we can see there's a direct connection to my y values and this. The other y transformation happens right in front, less so visible for a line. But if I have 3x plus 2, and I make a table of all my x values or y values, we're going to discover something interesting. So first of all, I should bring up my original line and just have some points on it. Make it a different color. And just have some points on it. Now, there's my original line. It's the standard line. And now I'm going to get rid of the plus 2. I'm just going to multiply the front by 3. And I'm going to look at the same x values. Minus 2, minus 1, 0, 1, 2. And I'm going to look at what happens to the y values. It looks like all my y values are now multiplied by 3. How does that compare to the original y values? Oh, it looks like it multiplied them all by 3. Let's click on some comparisons. This one's not going to change because 3 times 0 is 0. This one is 1, comma 1 on the parent graph. Let's multiply the y by 3. What do you get? 3. 1, comma 3. There it is there. Let's look at this one. 2, comma 2. Multiply the y value by 3. What do you get? 6. 2, comma 6. There it is up there. So it looks like this is a very visible and obvious transformation in that if there's a 3 in front of the graph, I multiply all my y values by 3 to figure out my new y values. You might say, well, why do this? Well, if you know the parent graph, and here's the parent graph, right? And even though those numbers are far away, and you figure out a transformation like that, and it's not doesn't make a lot of sense for the line because the line is so easy to graph, but it will for more complicated things. So if I have a line like this, and I know that's just simply y is equal to x, and someone asks me to draw a more complicated line of y is equal to x plus 4, I can just say, wait, that's just a y transformation. All my values of y have gone up by 4. So I'm going to just take, I'm going to take this one here, and the middle one, and this one over here. I'm just going to add 4 to all my y values. So I get minus 2, comma 2 is the bottom one. And then this other one in the middle, I get 0, comma 4. And then this other one over here, 2, comma 6. And now I'm just going to plot them, and I just notice, oh, wait a minute, these things are just going up by 4. But that doesn't matter. And I would plot this one here. The other one is kind of off the graph. Actually, let's grab more of the graph so that since I've added 4, I can figure out where it went. There we go. And we'll use this one. Okay. And remember, I'm just going to add 4 to the y values. That's all I'm going to do. For y is equal to x plus 4. And this is just practice and play. So if I add 4 to this, I end up at 2, comma 4, right up there. If I add 4 to this middle point, which is 0, comma 0, I get 0, comma 4, which should be enough, actually. And then if I add 4 to this 2, comma 2, it becomes 2, comma 6 up there. And now I can just take my line and draw it straight through. You might say, well, it would have been just as easy to do a T graph, T cell, and figure it out. And you're right. For simple lines, it would be easy. But for complicated transformations, it's not. And we're just working on the simple ones. So it's clear all I'd had to do was add 4 to my, if I knew my parent function, I could just add 4 to the y's and easily graph a transformation. Also be aware that you should always label your new lines so that you get full marks from your teacher and you're demonstrating your knowledge of transformations. So all I did was take the original points and add 4 to the y values and then plotted it. Okay, let's see if we can do the same thing. Let's say if I multiply this by 2, I have a line 2x. Or according to me, I just have to multiply all my y values by 2, and this is actually going to bring it down a bit. It's going to do a weird, what's called a stretch, a vertical stretch. And then if I take 0, 0, multiply my y value by 2, I get the same value. And then 2 by 2, if I multiply the y value by 2, I get 2, 4, which is here. And then if I draw a line straight through those, I get this. Notice this line is much steeper. It's going up much more sharply. It has a sharper slope. And it's called a stretch, a vertical stretch by a factor of 2. Because it multiplied all my y values by 2, made my line go up steeper. It stretched it upwards. By the way, an upward translation of 4, or whatever we did, that's called a vertical translation up by 4. If it had been -4, it would be down by 4. If it's called a stretch, it's called a stretch when the number is above 1. But let's look at what happens when this is y is equal to a half x. In other words, how do I graph a transformed graph if I don't want to graph a half x normally? How do I graph it from the original parent function? Well, I take all my y values. This is a y transformation because it's in front of the x. We'll get into telling the difference in a bit with a different type of graph. And I'm going to multiply all my y's by half. So what's half of -1? Or -2? It's -1. So it goes 2, -1. What's a half times -1? It's -1.5. So we'll go somewhere there. What's a half times 0, 0? It stays the same. What's a half times 1? It's 1, half. What's a half times this 2 here? I'm only multiplying all the y values by half. It goes here. And now when I draw the line, I discover a slope that's less steep, like that. This is called a compression. I've squished my graph downwards. I've squished all my y values down that way and made the slope less. This is called a vertical compression instead of a stretch. Compression by a factor of a half. But it also helped me plot it, and I could easily do it. Those are the 2 easiest things you're going to come across, y transformations. And I'm going to deal with one slightly unique y transformation. What if I had y is equal to -2x? Well, you take all your original x values, you just keep them. This is still a y transformation, but this time I multiply all my y transformations by -2. So -2 times -2, it becomes 2, +2. It becomes -1, positive. Oh yeah, I got to multiply it by 2. This becomes 2, +4. -1 right here multiplied by -2 becomes 2, +2. Sorry, 1, I got that first one wrong. 2, 4 right there. 1, positive, -1, +2. 0, 0 multiplied by -2 is still 0. So that spot stays the same. Then I get 1, -2 when I multiply this 1 by -2. And for this one, when I multiply the 2 by -2, I get 2, -4. And now look at this line. It goes like this. What happened with this line? Well, it indeed got stretched still. You can see that the slope is steeper than this one. But that negative, it looks like it flipped everything onto the other side. It flipped everything onto the other side. And this is called a reflection. And what's this axis called that we flipped on? In the x-axis. So that means when there's a negative number on a y stretch number or a y transformation, it's a reflection in the opposite axis, the x-axis. Even though this is a y transformation, it reflected everything into the through the x-axis, and it makes sense because all my y values switch to the opposite sign. And even though I've changed all my y values, the mirror that I went through is through the x-axis. So it's a reflection in the x-axis. Those are the easiest ones to understand. I cannot show you, using a line value, x transformations, because a line's just too simple. So what I have to do is I'm going to use a parabola. And you want to study the parabola a bit more, and you want to study that these are the 5 main points that you should learn. And I don't know why it's not lighting up. Let's just try it like this. Will it light up now? Yeah, it will. Good. These are the easiest points you should learn. And you should memorize them. And you should memorize the domain and range. But we're going to look at something interesting. We're going to keep that same graph around. I'm going to make a copy of it. And I'm going to open the brackets around this x. So this is going to be an x transformation. Now I'm going to add 2 to it. Now I'm going to turn off the graph. And you would think, okay, well, all that's going to happen is all my x values are going to move 2 to the right. This new graph, this whole thing's going to move 2 to the right. Oh, it moved 2 to the left. Okay, well, let's add 5 to it and see what happens. It should move 5 to the right. Oh, it looks like it moved 5 to the right. Left, rather. Let's look at some values. Let's just add 1 here and look at some values on this graph and compare them. Well, this is 0, 0. It's clear I'm moving to the left, so let's just subtract 1 from x and see if it's 0, minus 1, 0. It is. I subtracted 1 from the x values. What about minus 1, 1? What happens if I subtract 1 from that minus 1? I get minus 2, 1. Sure enough, the new value is minus 2, 1. What about this 1, 1? If I subtract 1 from the x values, I'm going to get 0, 1. Sure enough, the new value is, even though there, 0, 1. And we discover in here, let's add 3 and see what happens. So this was 0, 0. Let's subtract 3 from the x value. 0, it should be minus 3, 0. Sure enough, it is. What about here? Minus 1, 1. What if I subtract 3 from the x values? I should get minus 4, 1. Sure enough, I do. And you might say, well, why is it doing it? Why is it moving left? Okay, let's go back to the original, and I want you to ask yourself, what happens when x is 0 here? The y is 0. It's called the origin. But when I have x plus 2 in here, how do I create a y is equal to 0 out of this? Well, when x is minus 2 in here, that's when I create a y is 0. So that's why it moves to the left, because it takes a minus 2 x value to create a 0 y value out of this. In other words, to keep the vertex in the same spot. You'll discover x translations do the opposite of what you said. So for translations to the right, when you see a plus number here, it's actually going to be to the left. Just as the same way that the vertex here is the opposite. And you're just going to have to get used to and memorize that x translations do the opposite of what you think they're going to do. Turn off the graph. If you said to me that this is going to move 7 to the left, you are correct. It has moved 7 to the left. And to find the new points, all I would have to do is take that minus 2 and subtract 7, and I get minus 9, 4. And so there you go. It's minus 9, 4. So that means x translations, left and right, do the opposite of what's in here. What about stretches like we did in the last one? Okay, I'm going to turn this off. I'm going to get rid of this because it's harder to see. Now, if it's outside the bracket like this, that's a y transformation because it's not being affected. It's not affecting the x directly. It's outside the bracket. So this is actually a y translation. But if the 2 is inside the bracket, in other words, it's getting squared here, you might ask yourself, well, that would mean I multiply all my x values by 2, but didn't he just tell me to expect it to do the opposite? So here's my x values. If I multiplied them by 2, wouldn't that work? Well, actually, like the translations left and right, the stretches do the opposite. This is actually not going to be a stretch. What's the opposite of a stretch? A compression. It's actually going to do this to all the x values. It's going to multiply all the x values by half. Now, I can go into greater detail about why, but it's easier just to memorize it. What if there was a 3 here? Well, then it would multiply all the x values by 1 over 3. What if there was a half here? Let's flip this half upside down. What do you get? A half would actually create a stretch by a multiplication of 2. Let's do the half because visually it's going to be easier for me to multiply things by 2. So I'm going to put a half in front of this x like that. And according to me, it's going to do the reverse. It's going to multiply all my x values by 2. Let's do that. Let's change all these y values are going to be the same because there's nothing in here affecting the translation of the y. Let's multiply each of these by 2. I get minus 4, comma 4, minus 2, comma 4, comma 1 rather, 0, comma 0. So my vertex isn't going to change. 2. But keep in mind it's going to be a half. 1/2 x. It's going to be this. Let's see if I can get a picture of it. There it is there on the left. Right there. And this last one, so we got 0, comma 0, it didn't change. 1, comma 1, when I multiply my x by 2, I get 2, comma 1. And when I multiply this one by 2, I get 4, comma 4. So I should get minus 4, comma 4, minus 2, comma 1, 0, comma 0, 2, comma 1, and 4, comma 4. So I'm going to turn it on. And sure enough, you might say, hey, well, that looks like a y compression. It looks like it squished it downwards. Y. Yeah, x stretches look like y compressions. Y stretches look like x compressions. So this is actually an x stretch by a factor of 2. And to prove it, I'm going to show you some of the values. 0, 0 shared as predicted. But remember that this one, if I multiply the x by 2, I should see 2, comma 1 over here. And sure enough, I do. If I take this x value up here and multiply that 2 by 2, I should see 4, comma 4. And sure enough, I do, right there. As predicted, all my x values are being multiplied by 2 instead of a half. Kind of like the opposite. So again, consider that multipliers are reciprocal when trying to figure it out. And so you should actually think opposites for all the x transformations. And how do you spot x transformations? They're going to be right beside the x's with brackets. For instance, this one not only stretches it by 2, but I'm going to add, and you might say subtract. No, I'm going to add 3 to all my x values. Let's see if I can figure that one out without seeing it. Just going to take a picture. Now, here's the other thing for transformations. You do the multipliers first. So according to me, it's not going to be multiplying my x's by half. It's going to be multiplying all my x's by 2. And according to me, it's not going to be subtracting 3. I should add 3. So that means for each x value up here, I should follow this process. Multiply them all by 2, then add 3 to figure out the new x values. Okay, multiply this by 2, minus 4, add 3, minus 1. So my new spot here should be minus 1, comma 4. The y's don't change. Nothing happened to the y's. What about this one? Multiply it by 2. I get minus 2. Add 3, plus 1. So my new value here should be 1, comma, keep the y value 1. What about this one? Okay, well, the 0 multiplied by 2, nothing happens, but then add 3, I get 3. So my new vertex should be 3, comma, 0. What about this one here? If I multiply this 1 by 2, I get 2, and then when I add 3, it's 5. The y stays the same. So I get 5, comma 1. Notice that just as in the original, this was the vertex, and these repeated. These two will repeat. So you can almost guess what this next number is going to be. It's obviously going to be a 4y, but 2 times 2 is 4, and then add 3 is 7. Notice that they've all gone up by 2. That's because they were multiplied by 2. But let's see that these should be my new points. I'm going to plot them. Minus 1, comma 4. Minus 1, comma 4 is right there. Not going to plot them well, by the way. 1, comma 1. Oh, they share a point right there. 3, comma 0. Okay, there's the vertex. Starting to gain shape now. 5, comma 1. Okay, right here. And then 7, comma 4. Notice it still has that comparable point thing that these do. Notice also that it's also going to have an axis of symmetry, which we'll cover more in a bit, right down the middle. So I want to rewrite that last point, 7, comma 4, right there. Now I'm going to draw it in black. Now I've got to stretch it a bit because I haven't quite got it. That's close. There we go. I've successfully graphed this graph here without having to make a table of T cells, taking the original points from the parent graph, it's called the parent graph when nothing's happened to it, and following my rules of transformation, which will take practice and time. Fantastic. Now, what happens if there's a minus here? Uh-oh. That means I would have had to multiply them not by plus 2, but minus 2, which means all of them would have changed, and I can't do the same addition because it would have added differently. Well, we're going to discover that it creates a reflection in the axis, so all these points will go over here. In other words, I'm going to see the same kind of distance that way, but it's going to be about here. And it's going to be moving, it's going to be something like this. This isn't accurate, by the way, but you get a rough idea. It's going to look like that. So it reflects through the old y-axis that it started with. Let's see if that's true. Let's put a minus here and change everything we did on the left. And this time, with the minus, by the way, let's go back and confirm that we got the right points. I'm going to light this one up. And sure enough, I'll see there's my 3, comma 0. There's that shared point. There's my, right there, that's the comparable, minus 1, comma 4. Can't quite get to it. There it is. And then over here, 7, comma 4. So you can see that it's actually stretched the y-axis. It's gotten thicker, wider, and shifted it 3 over. So I had to multiply all the x values by 2 and then add 3 to them. All the y values stayed the same. This one's still 4 over here. That's still a 4, just like this one's a 4. So this point here is the transformation of that point. And this is called a horizontal stretch when it's less than 1. And it's called a horizontal compression when it's more than 1. And this is called a translation 3 to the right, because the minus 3 actually moves it to the right. And then we're going to now see what happens when instead I put a minus. I'm going to turn this graph off. Actually, I'm going to keep that one around. I'm going to make a copy. I'm going to turn this graph off, and we're going to see if we can predict what happens with a minus in front. Okay. Well, according to me, instead of multiplying by by 2, I'm going to be multiplying it by minus 2, and then adding 3. So let's multiply each thing by minus 2. That's 4, and add 3. I get 7, comma 4. The y stays the same. 7, comma 4. What about minus 1? Over here, when I multiply it by minus 2, it becomes plus 2. Remember, we're multiplying by minus 2 now. It becomes plus 2, and then when I add 3 to it, it becomes 5. Y stays the same. This other one, when I multiply by minus 2, doesn't do anything, but then I add 3 to it. It's 3, comma 0. This one here is minus 2, and when I add 3 to it, it becomes 1, comma 1. This 2, when I multiply by negative 2, becomes negative 4, and when I add 3 to it, it becomes negative 1, comma 1. Now you're going to see something weird here. Okay. So now I'm going to plot that. So I'm going to get 7, comma 4. And I'm going to do 5, 1. And 3, 0 is the same as it was. And I'm going to do 1, 1. Shares the same point again. And negative 1, 1. Oop, that one I did wrong. So times negative 2 is negative 4. Add 3, negative 1, 4. There we go. Right there. And then when I draw this, what's going on? What's going on? So I'm going to stretch it out a bit so I can match it. There. Okay, well, we're going to keep this one on, and we're going to turn this one on. How come it's the same? Well, all that happened is this is the axis of this one, and of the red one that doesn't have the negative, and all this negative did was flip it through this axis. It's affecting the x-axis, so it's a flip in the y-axis, except that this is its new axis. This is its new y-axis, essentially. So when it flipped, all these points jumped over to here and here, but they happen to be the same points. So visibly, that's not easy to see at all. And a lot of them, it's not. Like here's a line. And actually, a line's a bad example. Let's see if I can find a better one. Let's find an absolute value of x. There we go. And when I put the negative in it, you can't see it because it's flipping on the y-axis. All these points over here are jumping to this point, and this point is jumping over to there. So visibly, you can't really see it. If I put an x minus 3 here, let's see if I can see it now. Yeah, see? It's flipping around the same axis, so you can't really see it at all. You can definitely see it when we put it outside on the y. It flips upside down. So the problem is, these things are symmetrical. So you cannot see the flip that's actually happening. Let's pick something that's not symmetrical. So this isn't a great example because it's a cubic. But when I put the x in the bracket, let's watch what happens when I put the negative outside. It clearly flips on the x-axis, right? It's going down. Now visibly, this will be hard to see because it looks like it's flipping on the x-axis. But no, it's flipping through the y-axis. This would be easier seen if, let's see, we move it over a bit. So I'm going to put it on the outside. It's clearly flipping. And let's see if it actually might not work on the inside here because it's still going to have that axis there. Might be better if I somehow stretched it, or yeah. 10. There we go, nice and fat. Let's see what happens when I put a negative. I think it's still going to be the same thing because it's symmetrical. But at least this time we can sort of see a flip happening, right? It looks like it's the same flip, but actually here all the x and the y values are flipping. Oh, that doesn't work because it's got to be in brackets like this. All the x and the y values are flipping through its axis of symmetry, which is still here, right? So all the x values are flipping to the other side of that black line. Whereas when I put it out here, all the y values are flipping to the other side of the y-axis or x-axis. Tough to see when they're symmetrical. What about something that's not symmetrical? Let's see if I can pick a sine x like that. See if that's, oh yeah, I gotta do like that. Yeah, let's see, 4, 4, 4. Go from -1. Now, you might not be familiar with the sine curve, but it's just another function. And we're going to see what it looks like. There we go. Yeah, it looks like that. Now I'm going to flip with the thing on outside at the y flip, so it's going to flip in the x-axis. Flips upside down. Now I'm going to flip it inside near the x. It looks like it's flipping. So that problem is it's symmetrical again. I'm trying to pick one. They're all kind of symmetrical. That's the problem. Well, we'll see it more as we go. But essentially, you just follow those rules over and over again. Sorry to make that ending confusing. But you'll discover the reason we're learning the basic parents is these transformations apply no matter what function I do it to. And this chapter is going to be all about how to apply those transformations.